You step outside after a summer rainstorm and spot it in the sky, a perfect arc of colors stretching from one side of the horizon to the other. Red on the outside, violet on the inside, with every color of the spectrum neatly arranged in between. But here's something curious. Why is this spectacular light show always shaped like a bow? Why don't rainbows appear as straight lines, zigzags, or random wavy patterns? What invisible force insists on organizing millions of water droplets into this particular curved formation? The answer reveals one of nature's most elegant mathematical relationships, hidden in plain sight every time the sun and rain dance together in the sky. To understand why rainbows curve, we need to start with what they actually are. When you see a rainbow, you're witnessing millions of tiny water droplets acting as miniature prisms, each one performing the same light-bending trick simultaneously. Sunlight, which appears white to our eyes, is actually a mixture of all colors traveling together. When this white light enters a spherical water droplet, something remarkable happens. Inside each droplet, the light slows down and bends, a process called refraction. Different colors bend by slightly different amounts because they have different wavelengths. Red light, with its longer wavelength, bends the least, while violet light, with its shorter wavelength, bends the most. The light then bounces off the back of the droplet like a mirror and bends again as it exits, spreading the colors out even further. But here's the crucial part. This process only works at very specific angles. For you to see red light from a droplet, that droplet must be positioned about 42 degrees away from an imaginary line drawn from the sun, through your head, to the opposite point in the sky. For violet light, the angle is about 40 degrees. This means that red light can only reach your eyes from droplets positioned in a very specific set of locations around you. Now imagine you're standing in a field with thousands of water droplets floating in the air. Draw an imaginary line from the sun straight through your head. This becomes the center of your personal rainbow. All the droplets that can send red light to your eyes must be exactly 42 degrees away from this central line. If you mark all these positions, they form a perfect circle around you with the central line as its axis. Think of it like this. You're standing at the tip of an invisible cone, and the base of that cone, 42 degrees away, is where all the red light originates. The same principle applies to every other color, each at its own specific angle. When you see a rainbow, you're actually looking at the edge of multiple nested cones of colored light, all centered on that line from the sun through your head. This is why rainbows maintain their curved shape, because geometry demands it. The bow isn't just an arc, it's actually part of a complete circle. You usually only see the top half because the ground blocks your view of the bottom portion. But if you've ever looked down from an airplane during the right conditions, you might have spotted a full circular rainbow, confirming this hidden geometry. The implications are mind-bending when you think about them. The rainbow you see is entirely personal to you. Someone standing just a few feet away sees a completely different rainbow, created by a different set of water droplets at the correct angles for their position. Your left eye even sees a slightly different rainbow than your right eye. In a very real sense, no two people have ever seen exactly the same rainbow. This personal nature of rainbows also explains why you can never reach the end of one, despite countless legends about pots of gold waiting there. As you move toward where the rainbow appears to touch the ground, the angles change, and the rainbow moves with you. You're forever at the center of your own rainbow geometry. making the rainbow's end as unreachable as your own shadow. The physics gets even more interesting when you consider that some rainbows appear to have a fainter secondary arc above the primary one. This double rainbow occurs when light bounces twice inside the water droplets before exiting, creating a second set of angles. In the secondary rainbow, the color order reverses. Red appears on the inside and violet on the outside because of the extra reflection. You can create your own rainbow anytime you want by standing with your back to the sun and spraying a fine mist of water from a garden hose. The droplets will obediently organize themselves into the same curved pattern, demonstrating that this isn't some rare atmospheric phenomenon, but a fundamental consequence of how light and water interact. The consistent bow shape of rainbows reveals something profound about our universe, that beauty often emerges from mathematical precision. The same geometric principles that create rainbow arcs also govern the paths of planets, the structure of crystals, and the patterns of waves on water. In those moments, when you pause to admire a rainbow, you're not just seeing pretty colors in the sky, you're witnessing the elegant mathematics that underlies the natural world. The next time you see a rainbow, remember that its perfect arc exists because of your exact position in space and time. You're standing at the center of a geometric light show that has been precisely calibrated by the laws of physics, created just for you by millions of water droplets acting in perfect mathematical harmony. In that rainbow's curve lies a reminder that the universe operates according to beautiful, predictable principles, and sometimes, if we're lucky, those principles paint themselves across the sky.